quantum harmonic oscillator. We consider a quadratic potential given by expression in equation 1, which we know that in classical mechanics gives you a force that is linear on position. Therefore, the Newton's equation goes like this. And the solution in classical mechanics is a cosine, goes as a cosine with frequency omega, which is the square root of k over m. Therefore, most of the time, people write the potential in equation 1 in terms of this frequency omega. And so we are going to use this expression, which is 1/2 of m omega squared x squared. With this expression of the potential, the Hamiltonian has this form. Is that how it appears on books? And the Schrödinger equation, the stationary Schrödinger equation, considering that the momentum is equal to minus I h bar, the derivative of x, and we have to write h phi equal to e phi, have this form, right? This is how the Schrödinger equation looks with this potential. The first term is the kinetic energy. This is the kinetic energy. The other term is let's put another color. Let's take this. Is the potential, you see it here, and finally at the right, you have the energy times the function of the wave function. Okay, so most of the time when you are going to solve this the differential equation associated with the Schrödinger equation, what you do is propose a solution in terms of series, power series. So therefore, it's useful to have a dimensional equation. In order to do that, we will define a new variable psi that is adimensional and is given by this expression, which we call it 4a. You see, alpha 0 carries all the dimensions that should be in this case of distance, and we can solve for this psi variable and we get this expression. And with this formula, we can investigate how we can transform the derivative on x to a derivative with respect of psi. By the chain rule, we find this expression, right? That we can derivate with respect of x by derivating first with respect of psi and then multiplying by the derivative of psi with respect of x, as usual. So with these results, we can rewrite the equation as follows in expression 5, right? So it appears 1 over alpha naught squared downstairs in the first term, coming from the derivative, from the second derivative. And in the second term, we have a x squared that we can use 4b to substitute this value, and we have this expression. Usually, what you do is divide, leaving like this, the term with the highest derivative alone. So we divide the entire equation by the term that is multiplying. So multiply the entire equation by 2 times m over h bar squared, alpha naught squared. So we get 1. We could also multiply by minus 1, but just to leave it as it appears on books, we will not do it yet. So we have this, the term with the second derivative, the term with the psi squared, right? This term with this coefficient, and in the right hand side we have the energy divided or multiplied by this term, right? Okay, so what we can ask for alpha to be any value, and it will be good if it can help us to simplify the term, the most complicated term, which is the second one here. So we ask this term to be 1, and that gives us this equation that is here. And if alpha fulfills this equation, that is alpha equals to a square root of h bar over m omega, this term will get to be 1. But we also need that alpha naught is a distance, right? So let's just prove that in fact it's a distance. So alpha 0 should be equal to, let's analyze its units, right? So we have alpha 0 has units of the square root of h bar, which has units of energy. Let's do it in the international system, which is units of energy for our joules, which is kilogram times meter square over seconds squared, times the time, right? Because h bar, it has units of action, so it has a second here. And this is divided by kilogram of the mass downstairs and 1 over s. Right? So this gives you, the kilogram goes away, the meter stays, and the seconds get cancelled with this. So we have meter square root. So we have units of distance. So it's a valid unit. This is a valid definition for alpha naught. I did it here also, in terms of the energy. So it has units of distance. And in the right hand side of this equation, we have this other term. Let me write it in another color, okay? In red, okay. This other term here, we can write it as energy divided by h bar squared over 2 times m alpha naught squared. So this term should be a-dimensional, right? Because this is an equation, and here in the left side, we have coefficients which are a-dimensional, so in the right-hand side, there should be also a-dimensional coefficients. So this is a-dimensional. This inspires us to define a variable epsilon given by this equation here, which is a-dimensional. E naught has units of energy and is equal to h bar omega over 2, or 1/2 of h bar omega. And so we have natural units. We have found natural units for distance and for the energy. So let me point it out here. So we have a natural distance. It's the distance that comes natural for this particular problem, but we also find natural energies or natural units for energy given by 1/2 of h bar omega. This is here, right? So they are the natural energy units. Okay, so the equation that we get by making this equation number 3 a-dimensional is equation number 6, and we need to solve it, and we are going to do it using the method called asymptotic method. Okay, so we have this equation, and we need to solve this equation, right? This differential equation. And we are going to use the asymptotic method. The asymptotic method is based on studying the behavior of this equation at infinity or at 0 sometimes, depending how it appears in the equation, and get inspiration to propose a solution for the equation number 6. Okay, let's do it. So, for example, let's take the equation 6 and we take it at infinity, the psi value at infinity. At infinity, the term here will lead, and we will make disappear this one because, this term has an psi square and this has a constant. So when psi is going to infinity, this term will vanish basically. So the simplified equation at infinity looks like this. Therefore, we propose a solution that when you derive it twice gives you something that is proportional to psi square. This equation, this function will do it. We calculate the first derivative that goes like this, and the second derivative will give you two terms, right? Because every time that you derive an exponential that is a square, has a square there, it will give you a linear term. So you derive twice and you get this expression. We don't care about how the explicit value of this. What we care is about the leading term, which goes like this, right? And we need that the leading term cancel in such a way that the equation can be fulfilled. So we ask for this equation to hold at infinity, meaning this one, right? And so we know that the second derivative, the leading term, has this expression, and we sum it. Okay, I change signs, right? I put minus and plus here, and we get this expression. We need that these two terms cancel at infinity. Therefore, 4 times a squared has to be equal to 1. So there are two possible solutions, a equal to minus and plus 1/2. Therefore, the solution at infinity can be something proportional to e to the psi squared or e to the minus psi squared. But, at infinity, this is square, so the minus infinity or plus infinity doesn't matter. The only solution that is physical is the one that has minus. The other one is not. You cannot normalize it because it goes to infinity. So the only valid solution has this shape, has this form. This gives us inspiration to propose a solution for the original equation. So this is our inspiration. And we got it from studying the equation at infinity. And with this inspiration, we propose an ansatz, and a smart guess solution for equation 6 that has this expression, right? The expression that solves the equation at infinity times another function to be determined. And the only thing that we ask from the solution, the function u, is to be regular in such a way that doesn't ruin or doesn't destroy the behavior that we already fit by the psi at infinity. So we substitute this equation 7, this solution 7, this proposed solution, the ansatz, in equation 6. In order to do that, you need to find the second derivative. So we derive twice. The first derivative will give you this, it's a product. U prime means the first derivative of u, right? And then we derive again, and will give you now 4 terms, because every time you do derive a product, give you as much as factors you have. So you get this expression, and we need to substitute this in the original equation that I write it like this. I just multiply by a minus, and I get this expression. By substituting, we will copy the second derivative term, just put a minus with a plus because, I changed the sign. So I copy the second derivative terms, minus psi squared, the function, times the function, equal to minus epsilon, the ansatz. Okay? In this expression, we can get rid of the exponential, right? Because it appears everywhere. Because when you derive an exponential, you get the same exponential times something. Okay? Also, there are terms that are equivalent. You see, the term with the second, with the psi square cancels with this one. So proposing a function that leads the behavior at infinity help us to cancel the most problematic term, the one that has a psi square. Okay. Therefore, we get this equation, right? Equation number 8. Right? You can see that this is true by, for example, you have this term that goes here, and these linear terms, they sum, and you have a 2 there, and I just move this to the left, and we get this expression, equation number 8. We need to solve equation number 8 now, right, in order to find the expression for u. We'll do that in the next slide. Okay, so we have this differential ordinary equation, and we solve it using series. So we propose a series, in a power series of the function of the variable xi as this. And so the first derivative gives you this, because when you derivate an exponent, you get this function. A power of the variable, you get this expression. You put k downstairs and then subtract 1. And the second derivative will give you this. And you can guess how the expression that you need for each of these terms. Here in the equation, you just have the second derivative, and you know the second derivative is alone. Therefore, you need to fix it because there is no variable that will multiply this exponent. So what I did is to change, in a sum, the index of the sum is a variable that can be named as we want it. So I name it k tilde, just because I can. And this is 1, right? This should be 1. It looks like 2, but it's a 1. Just let me fix it here. This is -1. I just changed the name of the variable because this is an index that has no meaning. And I define a new index, which is k again, in such a way that the sum begins at 0 and the exponent in the variable is xi again. And we get this expression, right? We need to change the index in all the coefficients, right? Okay, therefore, we have the expressions and we can substitute. The second derivative, we use the last expression for the second derivative, minus 2 times xi, the function, which is the expression that we have. Oh, it's the first derivative, so we need this expression. For this expression, we don't change anything here because it appears with, you see, it appears with an exponent -1, k -1, and it will be multiplied by xi linear. So the exponent will correct by itself. So we leave it like this. See, multiplying this xi, this will fix the coefficient here. And for the other term, we just substitute. We also define a new variable to make the algebra easier. We define 2 times gamma equal to epsilon minus 1 because it will make the sum easier. Okay, so we simplify this equation and get this expression. The sum runs over the same index, so we put it at the left, and we get this expression. Since each of these coefficients should be 0, we can get this relation. It's a recurrence relation. You see, it goes k plus 2. So all the even terms are related and all the odd terms are related. Therefore, we can write the solution as these 2 terms. I packed all the even terms and all the odd terms. Okay, so with this solution, this is the solution for u. Okay, I just copy here the expression that we have earlier. Here, this is the solution that we get. But remember that we asked that for u to be regular function, and this sum is not regular because it has all the powers, even or odd, of xi. Therefore, we have to make it regular. Remember, we asked for u to be regular. Therefore, we need to truncate this solution. In order to do that, we need that the coefficient here, this coefficient here, should be 0 at a given k. And in order to do that, k minus gamma should give you 0 for a certain k. That makes the gamma term, so we ask that k minus gamma give you 0 for a certain k, let's call it k prime. Therefore, since k is an integer, then gamma should be an integer. Okay? So this term should give you a 0, so gamma is an integer, including the 0. It can be also 0. Therefore, but we remember that gamma is equal to epsilon minus 1, and this should be an integer, but epsilon is the energy divided by the natural units of energy, and we substitute this in the later equation, and we get an expression for the energy. So energy is h bar omega over 2 times n plus 1, with n being an integer, positive integer, including the 0. Okay, n can be integer, right? Including the 0, right? For the polynomials that you get by truncating this solution, you fix first. You choose whether you wanted the polynomial to be odd or integer. If you want it to be odd, you kill the a1. If you want it to be, sorry, it's backwards. So if you want it to be odd, you kill the a0. You make it 0, and then you just put a1 to a number. That is basically, there is tables that gives you which a1 to choose. You need to choose, and what you get is the polynomials. These polynomials, right? And for if you choose to be for the polynomial to be even, you kill the a1. And you get these expressions for the polynomials. They come in tables, right? You can find them in tables or internet, whatever. And these polynomials are called the Hermite polynomials, and the solution finally is this one, where C of Cn is the normalization constant. And so we have the eigenvalues and the eigenfunctions for the harmonic oscillator. In class we saw plots. We have plots for both, right? What people usually does is to plot the. So we have plots already for this, but basically what people does is plotting the potential. You see the energies are like 1/2 of h bar omega. And then they grow by 1, so +1, +2, +3. It's a ladder. And each of these energy levels has a function that I can plot here. And the first one is h0 is just a constant 1, and it gives you a Gaussian function. The other term will give you a linear function, so it will give you something like this. I think it's backwards, sorry. Something like this, more or less, and so on, right? So you have the 3, 4, yeah. You can plot it, and actually I put a Python code in the page.